scientific death.
Molasses has a cultural reputation for being slow and harmless, but in January 1919, it became one of the deadliest forces in Boston's history when a 35-mile-per-hour wave of it flattened an entire waterfront neighborhood. The path to the disaster began in 1915, driven by the global demand of World War I. Industrial alcohol was a key ingredient in the high explosives filling these artillery shells, and that alcohol was distilled directly from fermented molasses. To meet this wartime boom, the Purity Distilling Company rushed to build a massive storage tank on the crowded Boston waterfront. The cylinder stood 50 feet tall and 90 feet wide, capable of holding over 2 million gallons of the heavy syrup. Because the liquid inside was a common household staple, the company treated the massive volume of fluid as a harmless commodity. The local residents lived right in its shadow, unaware that the physics of the tank had created a massive, unrecognized hazard in their community. The construction lacked even basic engineering oversight. Arthur Gell, the corporate treasurer in charge of the project, had zero structural experience and neglected to perform simple leak tests with water before the tank was put into service. This diagram compares the steel thickness required for a tank of this scale against what was actually used. The walls were only a half-inch thick, 50% thinner than engineering standards demanded. Furthermore, the steel alloy lacked manganese, making it highly brittle around the rivet holes. As the tank was filled, it groaned and leaked so badly that neighborhood children collected the seeping syrup in cups. Rather than reinforcing the structure, the company painted the tank brown to hide the leaks. In January 1919, warm Caribbean molasses was pumped into the freezing tank. This triggered thermal expansion, pushing internal stress to 36,000 psi, nearly the steel's ultimate strength. Corporate speed overruled basic material science. By filling the tank to capacity, the company had created a structure that was mathematically destined to fail. At 12:40 p.m. on January 15th, the brittle steel finally gave way. Witnesses reported a sound like machine gun fire as the rivets sheared off and shot through the air. This illustrates a gravity current. When a dense fluid column collapses, it rapidly displaces the less dense fluid around it, in this case air, generating a powerful horizontal surge. Because molasses is 1.5 times denser than water, stacking it 50 feet high created an immense volume of potential energy. The moment the steel failed, that potential energy converted into kinetic energy. The collapse generated a 25-foot-high wall of syrup that surged through the streets at 35 miles per hour. The momentum was enough to snap the heavy girders of the Boston Elevated Railway and peel back massive sections of the tank's steel plates, as if they were paper. While onlookers immediately suspected a bomb, the absolute devastation came from 13,000 tons of dense fluid seeking its own level, hitting with more force than the munitions it was meant to produce. The physics translated into human tragedy. Survivor Anthony DiStasio was carried on the crest of the wave like a pebble before the surge grounded him and rolled him through the debris. Molasses is a non-Newtonian fluid, specifically one that is shear thinning. This graph shows how its viscosity drops under extreme pressure, which explains why it was able to flow with such terrifying speed during the initial breach. However, as the warm syrup hit the freezing Boston air, a second effect took over. For every 10 degrees Celsius drop in temperature, the viscosity increased threefold, causing the liquid to thicken rapidly as it spread. Rescuers found a knee-deep trap. Victims like firefighter George Leahy survived the initial impact, but became ensnared in the thickening goo. As the temperature continued to drop, the molasses became so viscous that trapped survivors were unable to keep their airways clear. These unique thermodynamic properties turned a blunt force impact into a completely inescapable, suffocating environment for those caught in the flood. The cleanup required 87,000 man-hours. Fireboats pumped salt water to scour the streets, and workers used massive amounts of sand to absorb the syrup that had coated the neighborhood and turned the harbor brown. To avoid liability, the United States Industrial Alcohol Company claimed the tank had been sabotaged by a bomb planted by anarchists. Residents responded with a landmark class action lawsuit. They utilized early structural engineering analysis to prove that the failure was a result of the tank's internal stress rather than an outside explosion. the court-appointed auditor found the company liable, forcing them to pay over $600,000 in damages. This was equivalent to roughly $11 million today. This marked the first time in the state's history that corporate negligence was mathematically proven in court, rather than being dismissed as an unavoidable accident. The disaster led to an immediate shift in Boston zoning, removing heavy industrial hazards from densely populated residential areas. It also created a new legal precedent. All major construction projects now required the mandatory sign-off of a licensed professional engineer or architect. This local tragedy became a foundational case study for engineering ethics, demonstrating how math-backed building codes are essential to public safety. This shift made professional oversight a mandatory part of urban development. By proving negligence in court, the disaster turned the professional standard of care into the strict, enforceable legal code we rely on today.